Hey guys. So, we're continuing on. This is our last lesson in Unit 3. We're talking about power. So, we've already talked about energy and how much energy we can produce, and different types of energy, and transforming energy, and all that sort of stuff. Heat, thermal energy, kinetic energy, potential energy. But what about the rate of doing energy? So, how fast energy can be used or transformed or something like that? We call this the power. So, power is the rate at doing work or transforming energy, right? So power is either the work divided by time or the energy. And we know that by the work energy theorem, the change in energy is equal to the work, right? So these two equations are identical, right? And it's measured in a unit called watts. What's a watt? That's a bad joke. Sorry about that. So watts measures power, and because it's joules per second, that's the definition of 1 watt. A watt is a joule per second, right? So we have a definition here of power, right? Quite straightforward. Let's say we have a runner, and he's able to do, what's that, 460,000 joules, 460 kilojoules of work in 12 minutes. How much power does he able to generate? So we know his total amount of energy, right? So we know that the actual energy produced or work is 4.6 10 to the 5 joules. And we know the time, so we pretty much know everything. However, the time is in 12 minutes. And we can't just divide we can't just divide the energy divided by the time in this case, because we have to convert this to seconds. So that will be 12 minutes times 60, which will give us, what's that, 720 seconds. 12 minutes is 720 seconds. So therefore, power is equal to the energy divided by time. So that gives us, what's that? It's 4.6 times 10 to the 5 joules divided by 720 seconds. What's that going to give us? Give me a second here. All right, so grabbing a calculator, that's going to be 4.6 10 to the 5 divided by 720. So that's going to be approximately 640 watts. Okay, I'll give you an idea. What's that? That's like it's like a kettle, basically. Okay, you are able, when you're running, you are producing about the kettle's worth of energy. Interesting. All right, so there's a straightforward question here. You're given the energy, you're given the time. Just divide them, and we get an answer. Just watch your units. Make sure you have your units in your equation, so you remember. If we didn't change the units, we would have seen here it would have been joules per minute, and be like, whoa, wait a second, joule per minute, that's not a watt. So we'll have to convert the units. That's why we always put our units in the question as well. All right. Let's say we have a 45 kilogram student. He climbs a 3.2 meter wall. Sorry, 3.2 meter ladder against a wall at an angle of 80 degrees with respect to ground. He climbs it in 4.1 seconds. How much power does he generate? Okay, careful here. So we need to think about how much work he actually does. We know the ladder itself is 3.2 meters, right? And we know that the angle, this picture is wrong here because the scale is wrong, just to make our lives easier. That's 80 degrees. Okay, so we need to figure out what his actual, let's call it y, his height that he's able to actually increase. We know that he goes diagonally 3.2 meters, but we need to find out how much he actually goes up. So we're just going to use the sine of the angle here, because this is opposite, this is hypotenuse. Sine of my angle is going to be opposite over hypotenuse, which tells us then that the sine of 80 is equal to y over 3.2. So the actual distance that he goes up is 3.2 multiplied by sine of 80. What's that going to work out to? 3.2 times sine 80 gives us, let's go, 3.043. We're going to take a bunch of decimals because we know we're gonna round at the very end of the problem, but we need the decimals as we're running through it. So that's how what his actual height is that he goes up. The work that he's gonna have to generate is going to be equal to his change in potential energy, right? So that's going to be, let's call that delta U, change in potential energy, which is going to be mg, and his change in height, which is just y. So let's call that mgy. And we end up with, what are we going to multiply here? 45 kilograms multiplied by, what's 9.81 newtons per kilogram. And his height from the previous part of our question here, 3.043 meters. That works out to 1 times 45 gives us a answer of 1,344. This is work measured. That's going to be measured in. Remember the unit? It's work, energy, joules. Okay, so we know his work now. And last thing we need to do is power. So there's the work done. There's that was step 1. This is step 2. And now we're going to put that into our work divided by time equation. So that's going to be 1,344 joules divided by 4.1 seconds. So this person is able to generate 330 watts of power. All right, so this person that's climbing this ladder in 4.1 seconds was able to generate 330 watts. Now be careful here with what this means. Because the person isn't climbing directly up, right? They're climbing at an angle of 80 degrees. That means they don't actually use all their energy to go up. Right? We would have to include all the other extra thermal energy and stuff that we can't really consider, but just from a purely potential energy point of view, right, it's easier to go up a ramp than it is to go straight up and down. Right? So that's why we have this extra term, this sine part of it that we had to calculate first, because the ladder is not directly vertical. All right. So let's try this ourselves. Let's do a little experiment here. I want you guys in your house. Hopefully you have stairs in your house somewhere going into a basement or something. What I want you to figure out is how much power you can generate while climbing your stairs. So what you're going to do is you're first going to calculate the vertical height of your stairs, not the stairs themselves, not the length of the stairs, but what's the actual vertical height between the two levels in your house. Okay? Then you're going to get your maybe get a person to help you here, or try it yourself. Use your phone, use the stopwatch on your phone. Determine how long it takes you to run up the stairs. Then figure out your mass. Remember, in kilograms, so make sure that's in kilograms. Okay, many of you know your weight in pounds, but make sure that you calculate your mass in kilograms. Make sure your time is in seconds, and make sure your height is in meters. Right? And then we're going to use our new formula here to calculate our power we can generate while climbing a flight of stairs. And if you want to have some fun, convert that to horsepower. 1 horsepower is defined to be 734 watts. All right? So try this little fun little activity. Pause the video here and go run up the stairs. Okay? But carefully, as science, right? So write it down. There's a famous quote from Mythbusters. Mythbusters. Science is just mucking around, but writing it down. Okay, so pause it here and have some fun. All right, if you've done that, here's some questions. Just working out these things. I'll post these on the Weebly in a little minute. And before we move on, though, okay, we. Unfortunately, because we're not in the classroom, because this is room 229 online, not room 229 in real life, we have to do, we got to skip, not skip a couple things, but there's some labs that we can't do. And the end of this unit, there's a few things that I like to play with, some different simple machines. Simple machines are things like ramps, pulleys, screws, wheels, things like that, the basics of our machinery. Okay, and we don't have time to do that, so we're just going to do a quick little talk here about what a machine is and what sort of advantages there are to these machines and what trade-offs there are. So let's talk about a ramp, a simple ramp, right? We talked about that ladder in that last question. This is a thing that moves something up, right? And we have to move an object a height h. But because let's say an object is quite heavy and we can't lift it directly up, we have a ramp that allows us to roll it up it or push it up it or something. Okay? But when we think about what we're actually doing, work-wise, the work is going to be, just from a purely potential energy point of view, it's going to be mg times the height that I raise it here. Right? I'm going from the ground up to this new height. That's my change in height here. Right? So that's the amount of potential energy that I've gained. Now, if we think about it instead as the amount of work done as it pulls up this slope, right? That's going to be the force that we push up with multiplied by the distance. And that distance here is L, right? This is in this second view. That's our distance that we're having. Now, the force, because it's going to be pushing upwards, right? It's pushing down like that, but we're only pushing up with a piece of it. We're pushing up with a sine theta portion of it, the projection we can call it. Okay, so this is the force of gravity pushing down, but we're only pushing against this little piece, which is the sine of that angle. We're going to play with the actual mechanics of this in grade 12. But if you look at this, we're going to get this term here. This is L sine theta. And what is L here multiplied by the sine of the angle? Nothing but h, the opposite. Right? The hypotenuse times the sine of the angle gives us the opposite here. So that L sine theta is just h. So in the end, we end up doing the exact same work. So even though we are pushing the mass a much farther distance and requiring a lot less force pushing, we end up doing the same amount of work as if we just lifted it. So why the heck do we have a ramp? Why didn't we just lift it? Because it reduces the force required. Right? What if we're unable to lift it directly vertically? Right? We have a very, very heavy mass and we can't just pick it up. We put the thing on wheels and we put it on a ramp because it's easier. We reduce the amount of force. However, there's a trade-off with any machine. So we reduce the amount of force required, but we have to then increase the amount of distance that we travel. Okay? So we have to push it a farther way. It goes we have to push it a distance L instead of lifting a distance h. So the trade-off of having to do less, having to push less, is having to push it farther. But in the end, the same amount of work is done. It's just we don't have to do it. We just do. It's less intensive. There's less force over a longer period of time, or a longer distance. And this leads us to an idea that we don't really have to talk about, but it's a good idea to think about in terms of an engineering point of view. It's things called mechanical advantage, of how good a machine is. In the case of a ramp, it's how much I am actually pushing upwards. So this is my F weight, compared to my force that I'm actually applying. Okay, so if it's a lot less I have to push with, I have a good machine. Let's say it's a quarter of the amount of force that I require. So I would have a mechanical advantage of 4. Okay, and another way we can think about it is the ratio of L, how much farther I have to push it compared to how much I would have to have lifted it. So in that case, I'd have to push it 4 times the distance that I would have to have lifted it. Okay, that would have a mechanical advantage of 4. It's a unitless expression because it's newtons divided by newtons. It's just a quantitative number that allows us to say, is a machine good or not, right? If instead I had a steeper one, let's say this is root 2, it looks something like that. No, that's a silly number. Why would I use an irrational number? If that's 1, say this is like 2. Right? If I had if this is, only twice as long, I would have to still have a significant amount of force required, right? And in that case, it would be a less good machine. But I'd have to push it less distance. But what if I go way over here, a very, very shallow ramp? I barely have to push it, but I have to push it over a long distance. This would have a mechanical advantage of, let's say, like 10 or something. Okay? So it gives us a quantitative number that it tells us how practical is, not practical, sorry, how good is the machine? How much does it reduce the force required? Okay? So that's for a ramp. A lever, one of the most important, powerful things that we have, right, is a lever, right? If I want to lift something, instead of having to lift it up entirely, I can put a stick and then a fulcrum here. This is called a fulcrum. Okay, and it'll pivot around that point. And because I have a much longer lever arm on this side, RA is greater than RB. I have a much larger lever arm on this side. I have to apply less force because this is a little bit complicated here, but the torque is the lever arm multiplied by the force. This little tau here, it's the Greek letter T, it's called a tau. The torques have to be the same. The torque in this direction, torque is like a force on a circle. It's circular force. Okay, so this torque has to be the same as this torque. The pushing down and the lifting up force have to be the same. The circular force, the torques, have to be the same. So for them to be the same, then since the radial arm is much longer than the pushing arm, is much longer than the weight arm, we have a much smaller applied force. Right? And in this case, this ratio here tells us our mechanical advantage. So if, let's say, the applied force arm, RA, is twice as long as the weight arm, I have a mechanical advantage of 2 in that case. I have to apply half of the force that I'd actually require to lift it. Okay? So this gives us the mechanical advantage of a lever. And the last one I want to talk about quickly is the mechanical advantage of a simple pulley. Okay? Pulleys are great because they allow us to do two things. They allow us to change the direction of the force, and they also allow us to spread out force. So let's start over here with the simplest pulley. Okay, I have a weight that I want to lift, and it's difficult for me to lift it straight up. So instead, I attach a pulley here to it. So now the little guy here just has to pull down. It's actually mechanically, as a human, it's easier to do that than trying to lift it off the ground. It doesn't actually do anything in terms of reducing the force. It's still the same amount of force required. This has a mechanical advantage, in this case, of 1. It doesn't change the force that I actually pulled out. It just changes the direction. I am pulling up on the mass, but I am pulling down on the string. But if I now want to lift this weight with the pulley arrangement in here in number 2, I am lifting up on 2 strings and distributing the weight that's pulling down here over these 2 different strings. I'm reducing the force required to pull up here, let's call this Ft, compared to here the F of my load. Why did I put a W? Of my load. I'm reducing it by 2. So in this case, my mechanical advantage is 2. The easiest way to look at this is looking at the picture, how many strings are actually holding up the weight. In this case, I have 1 string here and I have a 2nd string here holding up the weight. Mechanical advantage of 2. But again, this one would be a bit tricky because now I can't, would I have to like build a platform so I can stand up here and pull on that? That's not a very good idea, right? So I want to again have the weight pulling down. So instead, I now have that 1 string here that I would have had to pull up on, I attach it to another pulley. So now the weight is going to be pulling down. But I haven't changed my mechanical advantage because only this string and this string are actually holding up my mass. Call that FL. This string is only changing the direction. So this pulley arrangement here in number 3 still only has a mechanical advantage of 2. It is more useful for us because I want to stand on the ground, as opposed to having to build some sort of platform, but I'm actually not reducing my force that I'm pulling on the string with. Okay? And the third one here, how many strings are supporting the weight? Let's start from the inside. Okay, so there's one. Then we go around. Okay, this one's holding up the weight. 1, 2, and 3. Those 3 strings are holding up the weight. That, as I go around here, that's not doing anything but changing the direction. This one now has a mechanical advantage of 3. Over here, how many strings are holding up the... Okay, so there's 1 there. Sticky to right in here. 2 there. Goes around, up, and over this pulley. That's a 3rd. And up and around and over that pulley. That's a 4th. So this one has a mechanical advantage. 4. Now, what's the trade-off? What's my trade-off when I have to pull on these things? I'm pulling a much heavier, I'm lifting a much heavier thing than I can. I'm reducing my force, in this case, by 4. If I can only pull on a string with a force of 1,000 newtons, I can now lift a mass of 4,000 newtons. That's what this mechanical advantage tells me. It tells me how much I can actually use this machine. But there has to be a trade-off. Just like if we go back here to our ramp, the trade-off was for the reduced force was the increased distance. So what's the trade-off for a pulley? The trade-off here is the increased length of string you have to pull. I have to pull, in this case, in number 5 here, I have to pull 4 times as much distance. I'm pulling the string. Let's say I have some distance that I pull the string. Let's call that my effort distance. Compared to my distance, the mass goes up. Call that dl. The effort distance is going to be 4 times the load distance. I have to pull 4 times as much string to increase the height of the mass. I have to do 4 times as much pulling to get something to be lifted by a certain distance. I have to pull at a lower force. Right, I'm pulling less. I'm not having to pull as hard, but I have to pull just much more string. Okay, so there's always going to be a trade-off with any of these machines. Just like with the ramp, there's a trade-off. You have to push it longer. With the pulley, you have to pull it longer as well. Okay, so there's a quick little introduction to 3 different types of simple machines. We would have done a lab on pulleys. It's actually a lot of fun, but incredibly frustrating to try to get all the strings to go around and measure everything. And there also would have been a ramp lab. But unfortunately, we can't do that. So just a quick little cursory introduction to some simple machines and the concept of mechanical advantage. All right. Well, that's it for today. And hope you guys are staying safe. Remember the rules. Stay safe. Stay home. Do physics. All right. Talk to you later.